What's up, Trig? This is Mr. Carlson, C Squared Mathematics, and we are on our last week of Unit 1. Two more lessons, 5.7 inverse and composite trig functions, and then 5.8 applications of trig functions. That's all we're going to do, and then we're going to review for the rest of the time. So, no bell work, just 5.7. This is a rather lengthy lesson, so I want to just kind of do a caveat here. There's two parts to the lesson, primarily. First of all, there's the inverse part, and second of all, it's the composite part. This lesson, what makes it long is not just because of many examples, but most of them are short examples, but also what makes it long is because the explanation behind it. The explanation behind it is very lengthy. Remember, I'm a mathematician, I'm a teacher. I don't just get to teach you the what and the how, but I also teach you the why. So I need to teach you why it works, and that's what takes a long time. So at the end of this video, if it's an hour and a half, if you're seeing like right now it's an hour and a half, I'm sorry, it's the only way I could do it, okay? Now that I can just record everything and you can just sit there and take it, right? So please bear with me. I'm trying to teach you the full strength of trigonometry, okay, even online. But I have to say that this lesson is probably the hardest lesson out of Unit 1, easily. This is the hardest lesson out of Unit 1. It's definitely not the most confusing lesson out of Unit 1. I think the unit circle is probably 5.4, probably the most confusing lesson if you're really struggling to grapple on to that mathematics. But this lesson is definitely a close second. I think I can explain this a lot better than 5.4, so let's get started. How are inverse and composite trig functions related to regular trig functions? That's a very simple question, but it's totally loaded. Okay, so that's our essential question for today. That's going to be guiding us as we go on. And then hopefully you can be able to evaluate inverse and composite trigonometric functions by using the unit circle, which we will be, and special angles, which we also will be. So inverse, what's an inverse? Well, inverse and composite functions are something that you learned literally right before our trig unit in Algebra 2.2. So I hope you remember a little bit of it, and we're going to be reviewing it in the next slide. But I love this meme. This is from Bird something. I can't remember. Sandra Bullock, something Netflix. But Bird Box, or I think it's Bird Box or something. Something like that. Awesome. What's the inverse of that? This. Everything else is covered besides the eyes. Okay, so everything else gets evaporated, everything else gets diminished except for that one part. And I love that because that's so true mathematically. So let's go through some inverse review to help you. So far, this is what we've done, guys. We've learned trig ratios and function values. Okay, so we learned that the function value of a trigonometric function is literally a ratio. So it's a trig ratio. We learned how to do that with acute angles, any angle, and any real number. So 5.2, 5.3, 5.4, we learned all of that. Now, right now, at this moment, what we're going to be doing is working backwards. Okay, so we're going to be working backwards. So I know sine of pi over 4 is radical 2 over 2. But what if I'm given sine of theta equals radical 2 over 2? Will you be able to say, yes, that theta, that unknown there, is pi over 4? That's what we're going to be doing. We're going to be solving now for the angle measure instead of the function value. All right? So let's review some algebra. What does the graph of y equals x squared look like? Well, kids, let's go to Desmos.com, okay, where all your dreams come true. Now this, I'm going to shut all this off. This is just our unit circle, of course. But let's go to y equals x squared. Okay, that's what our graph looks like, right? Now, what does the inverse of y equals x squared look like? Well, let's solve the inverse. What would we do? We would just, do that, right? Wrong, okay? What we would need to do first is switch the x and y's. So that is x equals y squared. And now we would do that, which would mean y equals plus or minus radical x. But here's the thing. Is it plus or minus radical x, or is it plus radical x? And which one is the inverse? Now, if you're saying, well, it's a square root, so it has to be plus or minus, Mr. Carlson, I agree with you. But the problem is this, okay? If we did the inverse right here, so y equals, okay, square root of x. What do you notice? That's kind of weird. Now watch what I do here. What if I do y equals square root of x negative? What happens? Okay, now just to make it a little bit more presentable here, let's do this. Okay, that's pretty. No, I like the little dots. I want to be adventurous. All right, now this right here, the blue is my inverse function. Okay, the square root of x. Now this right here, the red, is my x squared function. Now, let me ask you a very important question. Are you ready? Is this function, let's take this off here. Is this function an actual function? As it is right here, plus or minus, because this is plus, right? And then this is a minus. Plus or minus square root of x is an actual function. You should be saying no. Why? Because if I perform my vertical line test, it does not pass as a function. Remember, our vertical line test is if I do it and I can hit the graph at 2 different points on the same x value. So you have 2 different y values for 1 x value. That means it is not a function. So what do mathematicians do? Like any great mathematician, they make up stuff. I mean, clearly, right? What do? They literally just say, although if I square root this, it is plus or minus, never mind that. Let me just get rid of the negative. Okay? And so now this is my function. This is my inverse function. Because before, if I put it right here, the function doesn't exist. This is not a function. It's a graph, but that doesn't mean it's a function. It doesn't function like an equation ought to. Okay? This is a graph, but it's not a function. How do I make it into a function? I just take the negative off. So now when I put them together, okay, what's the inverse of x squared? Radical x, but positive radical x. What does this have to do, anything to do with trigonometry? Well, let's find out. What does the graph of the inverse look like? I already showed you. Now this is very interesting. What's the relationship between the domain and range? What's the relation? What do we do here? With algebra, what do? We switched, before we even square root anything, we switched the what? We switched the x and y. Why did we do that? Get it? Why did we do that? Because the x and the y in an inverse switches. So now with an inverse function, the x becomes a y and then the y becomes an x. Okay? So what happens here? The domain x's switch into the range, the y's. Which is why you have such a graph that looks like this, which is why you have kind of like a tilted graph, because the x's and y's, they switch. Okay? They switch. And so this is 1, but if I trail along these points, I could show it and prove it to you. I'm not going to do that. Okay, so yeah. All right, I'm going to erase this. Now let's get to our actual trigonometry. What does this really have to do with sine functions, cosine functions, so forth? So inverse sine function. Now pay very, very close attention to this graph, to this slide. Okay, I want to show something to you really quick. Ready? So this is your sine function, roughly. Okay, it looks something like this. Yes. Okay, this right here, your range for your normal sine function, y equals sine of x. Okay, your range is -1 right here to +1, right? You should be saying, yes, Mr. Carlson, you're right. Hooray. All right, now watch this. Ready? Inverse sine function denoted by sine of -1. Now we just say inverse. We don't say sine of -1. It's not the same thing. is the inverse of the restricted sine function. Okay? So read carefully. The inverse sine function is the inverse of the restricted sine function. Why did we restrict it? Why did we restrict radical x? We took off the negative part, right? In order to make it a function. Same thing here. We take off certain parts of my sine function when we find the inverse. And then, because I'm taking off certain parts, I'm restricting it to this. This is very important. Write this down. I'm restricting it to this. That is what makes the inverse sine function an actual function. Otherwise, it's just a nice looking graph. But I want to be able to perform math on it. In order to perform math on it, I need to make it into a function so it functions correctly. That's why it's called a function. Okay? So in order for it to function correctly, it has to pass a vertical line test. But as the inverse stands, just like here, I erased it, but just like the radical x plus or minus, it wasn't a function until I made it into a function. What are we doing here? We're making it into a function. Why? Okay, I'll show you why with the graphs in a little bit. So this is the function that I'm using, and this means this. Often I will write this. Okay, often I will write this. So notice what we did here. Look at that. Notice the y's and the x's change. So this is usually how we write it. So sine of x equals y, but look at that. Now it's flipped. So now sine of y equals x. Okay, so now we are solving for angle measures now. We're solving for angle measures, not evaluations, not side lengths. Remember, I told you 2.5 weeks ago, the most important thing about trig is to make sure you keep track of what's an angle measure and what's a side length. What you get out is a side length. But when inverse functions are employed, like now, what you get out is an angle measure, okay, not a side length. So now where this right here, notice how this said x, yes? Now this is saying y because it's flipped. And now this. Okay, this is now my new restriction. So what is this? This restriction right here. This restriction is technically my range restriction. This is my new range restriction. Now you're saying, really? Like x is going to ranges? Technically, yes. And this is what makes this lesson so confusing is because we're switching the x and y's, and then what's a range and what's a domain is really hard to keep track, okay? It's really hard to keep track. So we read it as y equals the inverse sine at x. What does this look like as a picture? So this is my normal sine graph. I kind of did the normal sine graph right up here. Now notice my domain down here. Why does it do that? Well, go away. Oh my gosh, it's not going to go away. Wow. Are you joking me right now? Oh my gosh. Okay, well, my life. That domain down there. See? What the junk? Okay, I'm going to get super like PO, dude. I'm just not going to touch it down there. You're going to have to look at the domain. It's negative pi over 2 to pi over 2, right? Negative pi over 2 to pi over 2. That's the domain. Now that right there, because it's sine, is my domain, the angle measure. My angle measure is the domain because it's regular function sine, just like good old Bill. That's what we've been doing for forever. Now, what if we restrict that function like this? We're restricting this function. You see that? We're restricting this function. Now watch. This, as a restriction, when I do the inverse, watch what happens. It becomes this. So now, what it becomes is flipped. Now, what happened to the domain and range? They flipped. See? They flipped. So now my range is my angle measures, and my domain is my side lengths. Okay, because negative 1 to 1 right here is a side length, guys. That's a side length. That's an output. all right? Just like on the unit circle, it's an output. Okay, this right here is my actual range, though, because it's the inverse. But when in my regular function, the angle measures negative pi all over 2 to pi over 2 is my domain. So the domain and range, they get flipped here. And now notice, does it pass the vertical line test? Absolutely. If we continued like this, would it pass the vertical line test? No. But thank our lucky stars, we don't need to deal with that problem. Okay, so that means we have restricted this sine function in order, we restricted the original sine function in order to produce an actual live function for an inverse so that we can work with it. Okay, that's what we're doing. And we're doing that with cosine and we're doing that with tangent. All right, doing it with cosine and tangent. Okay, sweet. Let's continue. Okay, these are really interesting. These how it switches between the domain and then the ranges here, because this right here was originally and they're using set notation here for inequalities. I like to use interval notation, but right here this would be -1 x to 1, or sorry, y to y, and that would be your technical range for your sine function. But for your inverse function, it now flips the x and the y there. They just don't write that. So they're restricting those two things, just like I'm showing you right now. Okay. And just to reiterate, this y right here is the same thing as the range. Okay. Now this is the range technically for my sine function, but this now becomes my domain for my inverse function. So like I said, it gets really tricky when it comes to what is domain and what is range. So I hope I explained that sort of well. I'm going to continue on, and then hopefully when I start showing you the graphs and start going through examples, we'll make it through. Okay. So now, what are some of the exact values? Now this is a very important slide, so pay attention. First of all, let theta equals the inverse of sine x. Okay, I will usually write this. Okay, sine of theta equals x. Okay, I don't really like using this that much, although it's still correct mathematically. Usually I have found students are more prone to understand what the inverse is when I write it like this. You're like, oh, so we don't know the angle measure. Yes, okay, we don't know the angle measure. That's precisely what we're trying to find. And then we write it like that. And that's exactly what we do for step 2, okay? And that's why I like doing that. That's exactly what we do for step 2. But usually Math Excel will kind of give you this. That's what makes it confusing. I jump that gun and just go straight there. Now, what is this? This little guy, this little piece. That is a restriction. It means the exact same thing here, okay? So one is inequality notation, one is interval notation. This is inequalities, of course, because it has inequalities. This is interval notation because of the brackets. Now, what does this mean? Well, your theta here is technically your range, okay? Now, in your inverse function, your theta becomes your range, which means this, like I said, in your inverse function, it becomes your range. Now, technically, this would be your domain because it's an angle measure in your regular sine function. But because it's an inverse, we're switching the range and domain. We're switching the x and y's. So now it becomes a range. Okay? So this is your range interval. Awesome. Now, what does that mean? It means these are the exact values. If your inverse sine function is restricted to only exist between these two values, between these two values, negative pi over 2 to pi over 2, that means you only have a couple options on your unit circle. Really, you only have these options. So I would be writing this table down. Okay, this table is very beneficial. Now notice one thing before I actually give you a trick to help you understand this. Okay, notice one thing, it's negative. It's negative angles. It's negative ranges here, right? So it's negative ranges, negative pi's, negative radians. Okay, and so what that means is it actually goes down on the unit circle. Okay, it goes down on the unit circle. What does that mean? That means it starts already being down and it goes up. What does that mean? It means this. What are you going to use? You're going to only use the right side of the unit circle. The right side of the unit circle. So I'm going to pull up the unit circle here. Whoa, that looks like, I'm going to keep it. That looks like an M. Okay, you're only going to use the right side of the unit circle. So let's go to Desmos. Let's pull this up. This is the unit circle, of course. Okay, this is the unit circle. All right, so now what's the right side? The right side is this. This whole like half. Okay, this right here, this whole half. That's the right side. Now notice, watch, this as I go down, this is negative pi all over 2. This is negative pi all over 3. This is negative pi all over 4. This is negative pi all over 6. Okay, and of course that's 0. And then this is pi all over 6, just like what I have. That's pi over 4. That's pi over 3. That's pi over 2. Okay, so now you're changing these values here. Because again, those values are outside. I'm going down. I'm not going all the way over here. Okay, I'm not going all the way over here. I'm going down. So I'm starting down and going like that way. Okay, and since I'm going down like such, I'm including negatives in my angle measures. All right, I hope that's clear. So what does that mean for us? Now look, watch. You don't really need, I want you to, but you don't really need to write this down. I encourage you to though, but you don't need to. Why? Watch. Sine of theta equals 1. That's what it's saying. Sine of theta equals 1. Or negative 1. Sine of theta equals negative 1. All right? Where on the unit circle, where I just highlighted, okay? Let's erase all this stuff. Where on the unit circle, where I just highlighted, gives you sine of negative 1. Now remember, sine of theta equals y, right? Cosine of theta equals x. So where I just highlighted, on the right side of the unit circle, gives me a y value, a point, okay, of negative 1 down here. Now, is that 3 pi over 2? Well, 3 pi over 2 is the same thing as negative pi over 2. If I do sine of 3 pi all over 2, it equals negative 1. If I do sine of negative pi over 2, guess what? It equals negative 1. You know why? Because sine is an odd function. That negative pops out. So then you have sine of pi over 2 equals 1. But since it's a negative, it pops out to make it a negative 1. Get it? So that means, what is sine of 3 pi over 2? The exact same thing as sine of negative pi over 2, which is exactly what we have here. So if it asks you, find me the angle measure of sine of theta equals negative 1, you use only the right side of the unit circle and you look at, okay, where's negative 1 for sine? Down here, right here. That's my y coordinate, right? That's my y coordinate. Since it's my y coordinate, that's negative 1, that's sine. What is this? I can't say 3 pi over 2 because it's not within my range. Okay, it's not within my range. It's not within it. So I need to use a value that's within that range. Hence, the table comes very handy. Okay, and of course, when we get to the positive angles here, guys, this is exactly, literally just the trig table of common angles verbatim. Pi over 6, pi over 4, pi over 3. If we go over here, we go over pi over 6, pi over 4, pi over 3, 1/2, radical 2 over 2, radical 3 over 2. 1/2, radical 2 over 2, radical 3 over 2. It's the exact same thing, okay, because it's the first quadrant. So what does this mean, guys? This means right here, what I boxed, this is quadrant 1. And then right here in red, this is quadrant 4. And both quadrant 1 and quadrant 4 make up what side of the unit circle? The right side of the unit circle, okay? And of course, this is a quadrantal angle, okay? A sine of 0 side length gives me 0 degrees or 0 radians, okay? I hope that makes sense. I'm going to explain it that detailed only now. So when we go through cosine and tangent, I'm not going to explain it that detailed. So I just wanted it because it's going to look almost exactly the same, just a little different numbers here. But I just want to explain that in detail. Now notice, just FYI, important parts. What's the important parts? The important parts are what I'm going to highlight in green. What should you know? A, use the right side of the unit circle when dealing with inverse of sine. Okay? And then B, this is the range. That's probably the most important things. You can get all this from the unit circle. That's really important and everything. Maybe the negatives kind of confuse you a little bit, but really the important things are what I'm highlighting in green. That's the key. Okay? Again, not going to explain it that in detail with cosine, but before we get there, let's actually do some examples. Okay? So let's erase. My nose is bothering me. Okay, let's erase. Find the exact value of the inverse of sine of radical 2 over 2. Now, remember, my range equals negative pi all over 2 to pi all over 2, inclusive. Okay, this is my range. This is also the same thing as saying the right side of the unit circle. So that's what I'm going to be saying, right side of unit circle. Okay, so what do I do? Well, I go to my unit circle. Well, what I could do is literally just go over here. Okay, what's radical 2 over 2? Pi over 4. Boom, done. That's your answer. Or I could actually use my unit circle. Let's erase all this jazz. Sorry, let's go. Okay, let's erase all this jazz. And now this is my right side of my unit circle. So this is the right side of my unit circle. Okay, so now what do? Well, I find, all right, I need this. This is the same thing as saying sine of theta equals radical 2 all over 2. So what is theta? Theta equals what number? That's what I want to know. So what gives me radical 2 over 2? Well, you're going to scan your little points here. Okay, what gives you a positive radical 2 over 2 on your y coordinate? Okay, because sine is y. Sine of theta equals y. So which one? There's only one right here. And what is that value? Pi over 4. So that is pi all over 4. Okay, so there's a couple ways you can do it. You can use your unit circle just straight up, or you can use the table that I showed you on the last slide. I'm probably going to be sticking more with my unit circle because I just want to, that's a go-to one-stop shop. Okay, now let's go to this one. What is this saying? Well, it's still the exact same right side of the unit circle. It's sine, right? And it's restricted. That means it's restricted to negative pi over 2 to pi over 2. So I'm not going to rewrite that. But what this is saying is really sine of theta equals negative 1/2. So what is this saying? What is theta? That's what we want. So what angle on the right side of the unit circle of sine gives me negative 1/2? Let's find out. So negative 1/2. Not there, not there, not there. I'm only looking at y coordinates right here. Okay, I'm looking right here. Now, watch. This is 11 pi over 6. Is 11 pi over 6 within the interval negative pi all over 2 to pi over 2? No, because how to get 11 pi over 6, I need to go all the way over here. I can't go all the way over there. I can't even go over here because if I go over there, that means I'm breaking the half circle, the right side of the unit circle, right? So I can't do that. It's not 11 pi over 6. But if I go down, it's reference angle. If I go down the reference angle, and this reference angle is pi over 6, and if I go down, that means I get not 11 pi over 6, but negative pi over 6. And then I could also, like I said, I could also just go back and say, okay, this is negative 1/2. You see this? You could go back right here, this table. You can already copy it down right now. So this is negative 1/2. What's the angle measure? Negative pi over 6, right there. Okay? So you can use that table on this slide. If you copy it down, you could definitely use that. Or you can just intuitively just know that it's negative pi over 6 by using the unit circle, saying, okay, it's not 11 pi over 6. How do I do this? Okay, I go down pi over 6. I go down pi over 4, and so forth. And you can find it that way. Okay? Hope that makes sense. Let's go to cosine. Again, I'm not going to explain it that detailed with cosine, so this is actually going to be a lot faster, I promise you. So cosine, very, very similar, right? It's going to be the exact same thing, but now we're going to be using different kind of things. So notice that this is my cosine function. This is my initial restricted domain. Notice how it's angle measures right there for domain. And then, of course, this becomes cosine of y equals x, or sometimes what I call cosine of theta equals x. All right? Sometimes I'll write it like that. And then, of course, these get flipped. So this right here gets flipped. Notice that. So now my angle measures, instead of attached to my domain, my x's, my angle measures attached to my y's, my range. Okay? Just like I explained with sine. Right? And the same thing here. This is the restricted cosine function. Cosine, not the inverse. This is restricted cosine. Notice 0 to pi, 0 to pi. Right there, 0 to pi. And that's my domain. And then this is my inverse restricted cosine function. Now notice my domain and my range have flipped. As soon as that freaking exit thing goes away. Go away, thank you. Notice my domain and range have flipped. Wow, that's my domain and range have flipped. Okay? Notice that. Same thing, same exact thing. So let's erase. Let's go to a couple examples after I give you the table. So this is your table right here. Okay, this is the table that we're going to be using. Same exact thing right here. Theta equals inverse of cosine, or we can say theta equals inverse of cosine as inverse of cosine equals, cosine of theta equals x. Now this right here is my range. Okay, this is my range now. And just like before, and this is the same thing. So this is interval notation, which I'm going to be using a lot, and this is what we call inequality notation. They mean the exact same thing. Aren't you glad that you have a math teacher that tells you they mean the exact same thing? Now, what does this mean? 0 to pi. Well, is it the fourth or third quadrant? No. 0 to pi is right here. 0 all the way to pi. So what is that? The top half. So that means right here, we're going to be using what we call the top half of the unit circle. Okay? So that's the most important part, the top half of the unit circle. And these, of course, are your values, but guess what? These are the exact same values that you already have on the unit circle. You already have these values also on the trig table of common elements. Okay, so really, you have all this. This is really what it's saying, guys. This is all the values right here that I'm kind of isolating here. You see that? Maybe you have to squint, maybe make the screen a little bit larger. These are the exact same values. 1, radical 3 over 2, radical 2 all over 2. 1, radical 3 over 2, radical 2 over 2. I mean, it's the exact same values here. So we can actually, cosine is really easy because there's no negative angles, right? So we really just have to use the unit circle. We have to use the trig table of common angles. We can use this, or we can just, hey, what's the x value, x value, x value, x value, x value? Remember, cosine of theta equals x. So that means I'm just using my x values, right? I don't care about the y's at all. Okay, now, are we ready to go through a couple of examples? Yes, Mr. Carlson, we are ready. You kids, always wanting to learn. Breaks my heart, in a good way. Inverse cosine of negative radical 3 all over 2. Now remember, just letting you know, this is from 0 to pi. That is my restriction. This is the top half, okay? So that's the top half of the unit circle. So what does this say? This says cosine of theta equals negative radical 3 all over 2. So What does theta equal? Well, let's find out. What value, what angle measure of cosine gives you radical 3 over 2 on the unit circle? Well, that's not radical 3 over 2. That's not radical 3 over 2. Negative. That's not negative radical 3 over... That's not... Oh, here it is. Negative radical 3 over 2. Is that what you wanted, Mr. Carlson, as cosine equals x? Yes! And since it's within my little green bubble here, that is my angle, 5 pi all over 6. So I'm going to write that down, 5 pi all over 6. That's my angle. Boom! Okay, my seat is kind of like rocking back and forth. Kind of hate it. Just letting you know. What is this? This is cosine of theta equals negative 1/2. So what does theta equal? Let's find out. That's not negative 1/2. That's not negative 1/2. That's not negative 1/2. Oh, this is negative 1/2. Is that what you mean where cosine equals x? Yes. What's my angle? 2 pi all over 3. So 2 pi all over 3. Boom. Done. Easy. And I could have just as easily used the table that the slides in the last slide gave you that I posted there. Or you can just use your unit circle. Or you can use your little trig table right here. Okay, either way, okay, you would still get the exact same answer. Okay, now let's go to tangent. Tangent's going to be very different, but it's very different than cosine, but very similar to sine. Okay, so this is my tangent function. Now this right here is my domain. Now notice this domain of my tangent function gets switched into the range for my inverse function. Okay. Now this is very interesting. Why is that? Because my range, my initial range for the tangent function was negative infinity to positive infinity. Remember, my tangent function looks something like this. Okay, kind of like an x cubed. It looks something like that. It's pretty intense. It goes up forever. Okay, bottoms up. It exists down here for range. So when I switch the range, the y value of my regular tangent function to make it into an inverse, my x's will still be, negative infinity to positive infinity. Okay? I don't want to explain too much there because I feel like I'm kind of belaboring the point with the inverses. So now let's get to my exact values. So same thing, theta equals inverse tangent x. So this is really what I'm going to be writing out all the time. This right here is your range. It's the exact same thing as here. Now notice this is still the top half. No, sorry. Sorry. I'm going to fix that. It's not the top half. It's the right side. It's still the right side of the unit circle. Okay? Just like sine. So sine was the right side of the unit circle. Cosine is the top half of the unit circle. Now this is the right side of the unit circle. However, watch. It's not equal to here, okay? So sine was equal to there. It's not equal to here, okay? So it's not going to include those, that negative pi over 2, or it's not going to include pi over 2, whereas sine did, all right? So we still have the negative angles here that we have to deal with, but we can deal with them just fine. And we can use the unit circle, not the top half right here, but we're going to be using the right half. But I'm not going to be including these angles. So watch what I'm doing here. Okay, I'm not going to be including those angles for tangent. So tangent doesn't include those angles. Okay, so don't include that. Don't include that. Everything else in the middle, these 6, and that one, these 7. Sorry, go. Just like this. This is 7. 1, 2, 3, 4, 5, 6, 7. Just like here. 1, 2, 3, 4, 5, 6, 7. Everything else in the middle goes. Okay? Hope that makes sense. Okay. Now, let's erase this. Let's go to town. Example. What is this saying? Well, remember, my inverse has a range of brackets, negative pi all over 2 to pi all over 2. Not brackets, parentheses, sorry. That's the right side of the unit circle. So what does this mean? If this is my range restriction, okay, that's my range restriction. That means I have tangents of theta. Now, if you're asking, why is it still range if it's an angle measure? Because that's what you're getting out. you're technically putting in this function in side length, and what you get out equals has to be an angle measure. And in that case, the angle measures are ranges in this case. So what this actually says though is this. So what is theta equal? Okay, theta equals, we want to find radical 3. So this is where the unit circle kind of frustrates a lot of students, because tangent's not on here. But you know where tangent is found? The trig table of common angles. Okay, so tangent right here, what we're really using is this. So we're really using all of this function, but I'm not going to use that. And then I'm also using this right here. So those are the only values that I'm using for tangents, if you can see that. So negative radical 3, which in what I circled, what gives me positive radical 3. Positive radical 3. In what I circled, what gives me positive radical 3? Well, that's right here, which is pi over 3, of course. So you can use your trig table of common angles to also find that out. So this is, whoops, I almost did a radical. This is pi over 3. Now, again, the reason why I did the trig table of common angles here, because tangent's already given to you, whereas on the unit circle, you have to derive tangent by doing y all over x. So tangent is y all over x, and right now, tangent's not found anywhere here. You would have to divide your yx, divide yx, divide yx, and so forth. But it is pi over 3, because if I take this y right here, radical 3 all over 2 divided by 1/2, my x, the 2's go poofy, and I'm left with radical 3, which is exactly what we wanted. So my answer was pi all over 3. Okay, so let's try to do, I'm going to erase this. Let's try to do this one. Try to do that one by yourself. Just pause the video if you need to. I'm going to write down the answer soon, but I really want you to try to do it by yourself. So if you're like, this guy, who does he think he is? Do it. Try to do it by yourself. It's really easy. Go to the unit circle, go to the trig table of common angles, find negative 1 in here. What is it? You should all be saying that value. What's that value though? That value is 7 pi over 4. Is 7 pi, and this is what's tricky, okay? 7 pi technically within my interval. My interval, remember, is negative pi over 2 to pi over 2. Now, 7 pi all over 4 is way past that interval. You can't do that, okay? So this is where the unit circle actually is helpful, because when I go over here, I know, okay, so I'm looking at negative 1. All right, so negative 1. I know it's 7 pi. I know I have to go all the way over here to 7 pi over 4, right? So 7 pi over 4. But I can't do that because that's way past my interval. So what do? Instead of going that way, you have to go down. So if I go down, what's that value? Now, this is the tricky part, guys. I know it says 315. And 315 in degrees is the same thing as 7 pi over 4. But how much did you go down? You went down 45 degrees. A negative 45 degrees, which is a negative pi over 4. Okay, so this is theta equals a negative pi over 4. This is what makes it, I think, so tricky here. The negatives, okay? Now, of course, if you plugged it in Desmos, I haven't even shown you this. Watch. If I plugged in the inverse of tangent, you guys are going to kill me. If I plugged in the inverse of tangent, now notice I'm in degrees, okay? And if I plugged in negative 1, I still get negative 45, which is negative pi all over 4. So this is the second thing that I'm going to show you, and it's how to literally plug it into your calculator, okay? How to plug it into Desmos specifically. So you could just do everything that we just did, you could have just done on the calculator. And you're like, really? Yeah. And I wanted to explain it by hand because it's you need to know how to do it by hand, especially with the second part of this lesson, which is composite functions. By the way, we're still on the first part of the lesson, okay? So yes. So let's erase this. So this is a helpful screen. And the reason why this is helpful is because it literally just, it challenges you to understand really what trig is about. So there is a difference between domain restrictions and period cycles. So remember, the period of sine and cosine is 2 pi, okay? An interval in which non-restricted functions graphs complete one period. It's 2 pi. With tangent, it is pi, okay? With tangent, your period is pi. It repeats one whole period pi because then it's undefined right here. I can say that is true. So it's undefined. So this is one whole period, undefined, one whole period, and then it goes to 0, and then one whole period, undefined, and so forth, goes to 0. So what does that mean? Okay, what does that mean? It means this. Let me erase that. Let's go back here. It means these are not the same thing as the domain of the restricted function with inverses. So this is inverses. This is just something that we've already, all of this is just something that we've already learned. Okay? This is brand new stuff. These are the domain restrictions for inverses of sine, cosine, and tangent respectively. Okay, so this is the inverses, the domain restrictions. Okay? So know the difference. Do not confuse domains with restricted trigonometric functions with intervals on which non-restricted functions complete one cycle of their period. Okay? I thought that was helpful to include. And this is just kind of summarizing everything we did. So, summarizing everything we did, this is the graph of the inverse, graph of cosine, graph of tangent. Now notice this is negative infinity to positive infinity for my domain because it's kind of like flipped like that. Yeah, okay, it's just kind of flipped. And so notice that, but also notice, pretty cool, is that my actual function is this, and this actually reflects across what we call the y equals x line, or what we call the identity line. And this identity line is the thing that kind of, same thing with y equals x squared, and then your function right here. They flip across this like line here, where its slope is 1 and then the b is 0. That line, literally it's a line. And that's the identity line because that identity is what gives it an inverse. Okay, so if it can reflect across the identity line, then it has an inverse. That's something we learn more in pre-calculus, not in trigonometry, but it's still interesting to kind of preclude that or include that. Okay, now calculators. First things first, actually, before we get to calculators, number one, I need to say this every single time, especially if you have a TI-36X Pro, okay? This thing right here, inverse of sine, okay, of theta, does not equal cosecant, okay? It does not equal that, okay? Instead, cosecant of theta equals 1 all over sine of theta. Or another one, let's use another one. So inverse of cosine of theta does not equal secant. Okay? Instead, what I have is secant of theta equals 1 all over cosine of theta. So I just need to make sure you remember that when plugging in. Now, if you're using Desmos, there's no problem, right? There's no problem because Desmos has those functions available. But if you're using a TI-36X Pro, excuse me, they don't have such functions available. They don't have your inverse functions, or sorry, your reciprocal functions available. Okay. Now we're not going to do the inverse of the reciprocal functions, so don't worry about that. So let's find this. I'm going to just straight up use the calculator. I'm going to use Desmos. So inverse of sine of 1/4, and we want to do decimal places. Okay. Now it doesn't say degrees or radians, so I'm going to plug them in both. And I'm just going to have you guys copy down the answers when we're on Desmos. I'm not going to come back here. Okay? So make sure you get this down. I'm going to go to Desmos. I'm going to type both of them in, find degrees and radians. And then we'll go to the next slide. Okay. Inverse the sine of, actually, let's do b first. Now I already have tangent here. So this one's negative 9.65. So again, we're in degrees. So this is your answer in degrees. I mean, it's literally that easy. If you wanted to know where the function is, you go down here, function menu at the bottom, and then you would hit functions, and then you would click on the inverse function tangent right there. Okay. Now this is it in this is it. All right, this is it in degrees. If I wanted it in radians, notice how it's switching here. So notice how it's switching. Okay. Also notice this. My little thing is switching too. Isn't that pretty cool? Yeah, that's pretty cool. All right. So that's my answer in degrees. I'm going to leave it in degrees. And my other one was inverse of sine of 1/4. Okay, and that's what it is in degrees. Okay. That's what it is in degrees. If I wanted to switch it to radians, switch it to radians. That's what it is in radians for both. This is what it is in degrees, 14 degrees, roughly 14.5. Okay, so we can use inverses, and we've already kind of dealt with inverses previously in 5.2, 5.3, just a little bit with some trig functions. It is something actually that you did learn in geometry, or you should have learned. It's something that's very basic to find your angle measure. But this is how you do it on the calculator. Okay, awesome, awesome, awesome. Now, let's get to composite trig functions. All right. Now, I'm going to give you all this. I'm going to explain it. Okay? After I explain it, we're going to get to review some composite functions. Okay? So, this slide is very important. I would, if I were you, write down every single bit of this slide because it's very, very important. Okay? I would write down every single bit of this slide. Okay. What are these? Well, these are my restrictions. That's the first thing. So I'm going to say this. Off this side right here, these are my restrictions. What kind of restrictions? Well, it depends. So this right here, your negative 1 to 1. Now notice what it's saying here. Okay, this is actually a range. Okay, now this is a range too. They're kind of like both ranges and domains. That's why you don't have this comes directly from your textbook. They don't signify what it is, like whether or not it's a domain and range. That's why they only say interval restrictions. Okay, but it's very, very easy to see if it's a domain and range. Just follow. So this is saying sine of inverse sine of x. That's what it says. Sine of inverse sine of x equals x. Now, why is that? Easy. What happens when you take the inverse of something? Let me ask you, what happens if you multiply that by 1/2? 1. What happens if you take x squared and then square root it? X. What happens? Same thing here. Goes poofy. X. Okay? Same thing here. Goes poofy. X. Same thing here. Goes poofy. X. Poofy X. Poofy X. Poofy X. Like, it's the exact same thing. Okay? So this slide, maybe it looks kind of confusing at the very beginning, but really it is not, because this is a really helpful slide because it not only tells us restrictions and when to apply them, but also tells us that this goes poofy, and it's literally just the nature of the inverse. Now, where to apply the restrictions? Now watch very closely. If you have an inverse function inside of your sine function, an inverse sine function inside of your regular sine function. So sine of inverse of sine of x equals x. The reason why it equals x is if, and only if, it only equals x if it follows this pattern. Okay? This right here is technically, I want to say your range. Yeah, I want to say your range. Now, the reason why it's your range is because, look, this is the outside function. This is the inside function. You are going to have to abide by the range of the outside function. So if this was like 5 right here, first of all, you can't take an inverse of 5. Why? Because whatever that equals, it's not that. You can't have an output of 5 on sine. Why? Because that's not a ratio. I mean, it's a ratio of 5 over 1, but it's not a ratio. It's past the output. And the output in this case is your range. So this is your range. Okay? But now notice here, this, which is why it's so tricky, guys, this is your domain. Why is it your domain? Because look in the inside function now. This domain, it needs to abide by the domain. But then again, it needs to abide by this. So in one sense, it is a domain when you plug it in. But it is a range when you get something out. And that's just so confusing. So I'm not going to go into that more than it needs to be, because to really study that takes a really brilliant mind. It takes, and you guys are just now learning all of this. So when we go through the examples, I'm going to try to make it as easy as possible for you and leave out all the technical jargon. Okay, all you need to know is this. So I'm going to erase all this. All you need to know is that if your problem looks something like this, that x needs to fall within that range. Okay, let's just say that. Okay, if the problem looks something like this, that x needs to look something like this. Like I said, range. So if you want to just use these as ranges, you can, but that's not technically accurate. And I'm just going to leave it at that. Okay, I'm going to leave it at that. Let's get into what a composite function looks like. This is review from Algebra 2.2. So this is what composite function looks like. Okay, and this is really what it is. If you plug in an inverse of an actual function, you just get x out. I mean, we do that all the time. That's what it is. So if I have y equals x squared, okay, or let's just say this. If I have f of x equals x squared, but then I have g of x equals radical x, okay, what is g of x? G of x is literally the inverse of f, right? So g of x is literally what we call the inverse of x, correct? Now what happens if I plug these into each other? What happens if I take f and then the inverse of x? What is that going to look like? That means I take that function and plug it into that x. So what it's going to look like is radical x, x, and then squared. But what happens? I just get x, which is exactly what you have here. Okay, you just get x. Okay, a more elaborate example of an actual without inverses, with an actual composition of functions, is this. If you have f of x equals 5x, and then you have g of x equals 10x plus 2. Let's just say that. And if I want you to find f of g of x, this is review from Algebra 2. That means you're plugging in g of x into that x. So it's going to be 5 times 10x plus 2, which is 50x, and then plus 10. Okay, that is how you do composition. Now, what I just showed you here on this side is composition of inverses. This is just straight up composition. Okay, so there's a difference. We're going to be doing composition of inverses, and because we have to do composition of inverses, we have to abide by the restrictions. Okay, so I have 3 slides left, and one of them is a checkpoint slide. Okay, so let's get to it. Let's get to it, Lars. How do I do these examples? First of all, you'll have steps. Step 1. You ready? You sure you're ready? You positive? Yes? Yes? Step 1. Check to see if x is in the given property interval. Very basic, but it can get confusing. Okay, but what you're going to be using are these examples. Okay, so these, you're going to be using these for the next slide. Got it? So this right here, this slide is directly correlating to the next slide. Okay? Okay. Step 1. Check to see if x is in the given property interval. If so, you're going to use that property. Good job. By saying use the property, I mean it's just going to equal x. It's going to equal that number. Okay? If not, you're going to evaluate the expression. So what will this look like? I'm given these questions. Let's get to it. So what is this? Okay, so first of all, our first thing is it in the property interval? Now, what does that mean? Well, the property interval, if I go back, the property interval is -1 to 1. Now, watch. Go back to the slide. I'm not going to keep going back. I want you to do this. Okay, replay the video. It's a little bit ago. Look at your notes. When you saw cosine of inverse cosine of x, it equals x. But the property interval is this. Okay? Got it? That's what I'm saying. And if you don't believe me, it's on my little key. Okay? If you can read. Yes? All right. So go back. Go back and see that this is your property interval, -1 to 1. Okay, it's the very first cosine. When it looks like this, cosine of inverse cosine of 0.6. What will that equal? Well, since 0.6 is in the interval, okay, it is within this interval, this range interval. Because it's in the interval, what's the next step? Use that property. Whoopsie. What does that mean by use the property? Well, it equals x. What is x in this case? 0.6. Okay? So again, this is what it looked like on the last slide. I want to try to reiterate this as much as possible. It looked like this, right? That was my formula. Find that on the last slide. Find that formula. This property interval was this. Now you're going to ask, okay, whatever that x is that between -1 to 1? Literally on a number line. Is it between negative, is it 5? Is it 10? Is it 0.25? The fraction is in between this. If it's 0, it's in between this. If it's -1/2, it's in between it. If it's 1/2, it's in between it. But if it's 2, is that past it? Yes. So since this is a decimal 0.6, that is going to be in between this range, okay? So since it's in between that range, and again, by range, I mean this, -1, 0, 1. It needs to lie somewhere on this number line. 0.6 is like right here. Is it in that number line? Yes. If it's in that number line, what's your answer? Whatever that number is your answer. You're done. Okay? And because I had a student that complained so much, hopefully she is watching all the way till the end, you get a unicorn, okay? That's the easiest example. That's amazing, okay? That's amazing. Okay. Now, what's the next one? This one. So let's go. Okay. Now, what the function looks like on the last slide is this. But only if, let me find it here. Only if it goes in between -pi/2 to pi all over 2. Okay? So this right here is my thing that I will find on the last slide. Now, you're going to look at x. What's x? Well, that's 3 pi over 2. Okay. Now, is x, 3 pi over 2, is that between -pi/2 to pi over 2? No, it's not. It actually isn't. Which means we're going to say not in interval. But does that mean, wow, that looks awful. I'm going to leave it. Okay. That means I'm going to evaluate that. What does that mean? I'm going to evaluate what's in parentheses. Okay. So that means I'm going to take sine of 3 pi all over 2. And what is that? Well, you just look at your unit circle. What's the y-coordinate? It's -1. Okay, so since it's -1, now when I am evaluating the interval, what is this? I'm saying now sine, inverse sine, of -1. which is the same thing as saying sine of theta equals -1. Now, where did I get this inverse? From my problem. So now I'm starting at the very beginning. I evaluate the middle and then evaluate inside. And now what I look at is right here. And so -1. So what value gives me -1 on sine within that interval? And we actually, I think we just did this, but basically it's just negative pi over 2. Why? Because if you go back in the previous slides, you'll see that on the unit circle, negative pi over 2 is right here. So it goes down, and this is not just 3 pi over 2, but this is negative pi over 2 right here. Okay? Negative pi over 2 and 3 pi over 2 are the exact same thing. So instead of using negative pi over 2, you change the interval to make it, or sorry, instead of using 3 pi over 2, you change the interval to make it negative pi over 2 so that it can fit. So this is my angle measure. Theta equals this. Okay, that's what we're trying to find. Now, let me ask you a question. You ready? Could you plug this in your calculator and can you get the exact same thing? Yes. Okay, you could definitely do that. I encourage you not to, but you could. Okay, you can plug this verbatim. If you're in radians, you can get that on the calculator. Now, let's go to the next one. Is this within the interval? Okay, now notice this is the exact same as this first one. So that means my interval is -1 to 1. It's the exact same as A, right? Now, is 1.5 between -1 and 1? Yes or no? Just hit it to me, give it to me straight. Is it between -1 and 1? You should say no, which means it's not in interval. So since it's not an interval, can we evaluate it? Let's try to evaluate this. I double dog dare you. Evaluate this. Give it to me straight. What is inverse cosine of 1.5? Do it. I'll just wait. You should get this. Undefined. Why? Because 1.5 is past the range for cosine. It's past the range for cosine. It cannot equal 1.5 because it's past this range. Okay? All right. So use the calculator to always double check if you need to. Awesome. Now, what if you had something that was like this? What's the difference between this and what we saw before? This you see as cosine and tangent, whereas before we saw cosine, inverse cosine in the same problem. And then another problem we saw sine and inverse sine. And another problem we saw, again, cosine, inverse cosine. So you had that property there that we used in 2 slides ago. Do you have that same property that we used 2 slides ago? No. So this slide right here, just to reiterate, this slide right here is only applicable when you have sine, 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 cosine, 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 tangent, tangent, tangent. When you're taking the composition of the inverse of the same trig function. So sine, inverse sine, sine, cosine, inverse cosine, cosine. You're not taking inverse cosine tangent, right? That doesn't equal x. Okay, you're not taking inverse sine cotangent. Okay, you're taking inverse sine sine, that equals x. So this slide only applies to these examples. Okay, the previous slide only applies to these examples. So what and how can we solve this? It's actually way easier. Okay, so I'm going to actually show you. We have to use 3.3 or 5.3 stuff to solve it. Okay, so let's solve it out. First things first, I like to always, this is just me, I like to always rename this. Cosine, and then tangent, inverse tangent is 5/12. So I'd like to just say this. Tangent of theta equals 5/12. Because this helps me understand what the 5/12 is actually, 5/12 is actually saying. It's a side length, okay? It's a ratio, right? So that means my second part is going to build an xy plane. But now notice, look at inverse tangent. Okay, inverse tangent. What is, for inverse tangent, actually I want to do it down here. Okay, What is the inverse tangent? What is my interval for inverse tangent? Okay, that's what I want to write. That's my second step. My interval for inverse tangent is negative pi all over 2, comma, pi all over 2. That is my interval, okay? So that means I'm restricted to quadrant 1 or quadrant 4, okay? So I'm either in quadrant 1 or quadrant 4. I'm on the right side of the unit circle, remember? So now step 3. I'm looking at tangent and I need to build it. I need to draw this sketch, okay? I need to build it. I know I'm either in the 4th quadrant or the 1st quadrant. Now, let me ask you a very important question. Are you ready? All students take calculus. I don't care about this stuff. I only care about this. Where is tangent negative and where is it positive? It's negative in quadrant 4. It's positive in quadrant 1. So only cosine is positive in quadrant 4, not tangent. So if tangent right here is positive, which quadrant are we in? It's got to be the 1st, which means my 4th and final step is to build the 1st quadrant. It's got to be the 1st. So build the 1st quadrant, just like what we did. This is theta, okay? So now that I build it, tangents ratio is opposite all over adjacent. And then I solve Pythagorean theorem to find what that value is. Some of you probably already have it memorized. It is 13. So technically, if you want to do that real quick, you can do 25 plus 144 equals r squared. And that will be 169 equals r squared. So r equals 13. Okay, that's just Pythagorean theorem. All right, so now that I have that, now ready? I guess this is the final step. My bad. Whatever. This is the final step. Now that I know what this is, now it's really easy. I can kind of sort of bypass all that and just go straight for the cosine. So now, what is cosine of theta? What is cosine of theta? Given all of this, well, adjacent over hypotenuse, baby. So 12 all over 13. That is my final answer. Now this one, these are a lot more fun. I find these so much fun because they're so easy. And by easy, I mean they utilizes really everything that we've already done before in the past. The only new thing is this right here, okay, the interval and knowing which quadrant it's in, okay? So really, I just bypassed that tangent because I already evaluated it by using this, the triangle, and now I can just find out, okay, what is cosine? So, sweet. Now, let's go to another example. Let's go to this one. First things first, I like writing it out different. So this is tangent of theta equals 3/4. Okay, second thing is first, my interval is negative pi all over 2 to pi all over 2. I want to look at my inverse of tangent. Third thing is third. Okay, notice how this is positive tangent. So same thing. If I'm stuck with the quadrant 1 and quadrant 4, it's got to be quadrant. Quadrant 1. So I'm going to choose that. And then fourth step is to build my first quadrant. So angle. So opposite 3 all over adjacent 4. This is a 3, 5, 4 triangle. So I know it's got to be 5. Okay. So since it's 5, now I just look at sine, and that's my fifth step. So sine of theta, which I don't care about, is opposite, which is 3 all over 5. Easy. Done. Boom. Okay? So let's move on to my very, very last one. Same exact thing. Let's do 1. This is cotangent. And then I'm going to do sine of theta equals, and then this is negative 1/3. My second step, I'm looking at inverse sine now, so now my interval is included, brackets, negative pi over 2 to pi over 2. This is still going to be the right side of the unit circle, just like tangent here, but now it's going to be included. And now 3, my third step, is going to be finding out, okay, if I'm left with all students take calculus, I can't use the third or second quadrant because I'm only stuck with the right side of the unit circle, right? So it's either in the first one or the third one, okay? Now, first one or the fourth one. Now, if this is negative, okay, if this right here is negative, this thing is negative, that means it can't be in the first because all functions are positive there. So that means it's got to be the fourth. So that means when I go over here, I blow up my fourth quadrant. So I go down, right angle, theta. So opposite over hypotenuse. Opposite is -1. All over hypotenuse, which is 3, which is always positive. I want to solve for the r. I will let you solve for it. I will just tell you the r for the sake of time. It's 2 radical 2. Okay, it's 2 radical 2. You can solve that whenever you need to, but it is 2 radical 2. Which means my fifth and final step, I bypass all that fun jazz and I just go straight for cotangent. Cotangent is adjacent over opposite. So adjacent, which is 2 radical 2, all over opposite, which is -1. So this equals -2 times radical 2. Okay? Sweet. Awesome. Okay. So that is literally the whole lesson. I know that was tough. I know that was long. Thank you for staying with me. Let's erase. Now, if you want to go through these checkpoints, you can. Unfortunately, because for the sake of time, I'm not going to give you the answers. I'm confident that you guys can go through with it. And so if you're like, well, if you're not going to give me the answers, I'm not going to write it down. Whatever. Okay? So be it. Try at least some. I'm encouraged. I think you guys can get it. Try some of them. So pause the video if you need to or if you want to. Get some down. But I'm going to move on to the summary. What did we learn? We learned lots of junk. Use the inverse of sine, cosine, and tangent. We used the calculator to evaluate inverse trig functions. We also found exact values of composite functions with inverse trig functions. And that was it. I think what I should have probably added is also used a sketch to evaluate composite functions as well. So, homework. 5.7, Math Excel. Make sure you are preparing for your homework quiz. Remember, if you have an 85% or above, you don't need to take the homework quiz. But if you have any partial credit requests on the homework quiz, if you take it beforehand, just send it to me. This is C Squared Mathematics. I'm sorry for the long video, but I hope you learned something. Peace out, Trig.